Introduction, I'd like to show a little video just to get started, where somebody else does some of the explaining and makes it easier for me to start my story. So let me see if this can be made to work. It's more or less ready. It's 4 or 5 minutes, so you may have seen it before, but in any case, it's fun to hear. So
the Royal Swedish Academy of Sciences has decided to award the 2016 Nobel Prize in Physics with one half to David J. Thouless and the other half to F. Duncan Haldane and J. Michael Kosterlitz for theoretical discoveries of topological phase transitions and topological phases of matter.
And today's advanced technology, take for instance our computers, rely on our ability to understand and control the properties of the materials involved. And this year's Nobel laureates have in their theoretical work discovered a set of totally unexpected regularities in the behavior of matter, which can be described in terms of an established mathematical concept, namely that of topology. This has paved the way for designing new materials with novel properties, and there is great hope that this will be important for many future technologies.
I will start by explaining to you a concept from the citation that might not be familiar to you, and that's the concept of topology. So I brought my lunch. Now, for us, you know, these things are very different. This is sweet, this is perhaps salty, different shapes, etc. But if you are a topologist, it's only one thing that is really interesting with these things in which they differ. This thing has no hole. The bagel has one hole. The pretzel has 2 holes. The number of holes is what the topologist would call a topological invariant. And just as you cannot have a half a hole or 2 2/3 holes, you can, for a topological invariant, only have integer numbers. So what does this have to do with physics? Well, if we go back to 1980, it was a beautiful discovery made by Klaus von Klitzing. He gave him a Nobel Prize in 1985, actually, for what's called the quantum Hall effect. What he did was that he took electrons, he confined them into a thin layer at very low temperature and at extremely high magnetic field. He found that when he measured the electric conductance in this system, he could see it came in steps. Nothing, or 1 unit, or 2 units. And this unit that he measured was to an extreme precision. So why could you get something which is so precise? There were ideas about that, but the real breakthrough came with the discovery of one of today's laureates, David Thouless, who could show that these steps here actually can be explained as such a topological invariant. It's not exactly as the number of holes in a bagel or a pretzel, but it's something very, very similar. And this also explains why it is so precise, why it's so robust, why you get integer steps. Duncan Haldane, another of today's laureates, showed that you could do the same without having this very strong magnetic field. And for the continuation of this field, that was very, very important. Let's move on to the next concept in this citation, namely topological states of matter. How do you go from a gas to a liquid to a solid? You do it, you lower the temperature. People believed that if you had these very thin layers, for instance, a thin liquid layer of helium, you would never have such a phase transition. That had been proven mathematically. But when people prove that something cannot happen, it might be that they haven't thought of everything. And the thing that they did not think of in this case was this thing. They did not think of, well, not tornadoes, but vortices. This is the artists rendering some layers of liquid helium. And you see, there are small vortices here. Here we have a blow up. You can see the liquid is whirling around here. Now, at very low temperature, these vortices always comes in pairs. Actually, it's one vortex going in this direction and another one going in that direction. It's a pair of vortex and anti-vortex. They keep together. When you raise the temperature a little bit, then what happens is that these super tight pairs, now they will sail away and they become free. And that is a phase transition, a completely new kind of phase transition driven by topological effects. This prize here is for theoretical discoveries. It has combined beautiful mathematical and profound physics insights and achieved unexpected results that has been confirmed by experiments. That's what the prize is for. It's really beautiful and it's deep. Having said that, this work has inspired lots of activity. In labs all over the world, international research, scientists are hoping for practical applications in new electronics, new materials, even perhaps components in the future quantum computer.
Physics.
It keeps talking. Sorry. This was Professor Hans Hanson, who's at Stockholm University. He's also, I think, at the moment, director of Nordita, and he's a member of the Nobel Committee, obviously. And I think he had the day of his life when he could explain, this year's prize with all his buns and bagels and pretzels. And in a sense, this was the best summary I could think of my program. So in a sense, my 10 hours here will be, putting lots of details onto this story. But my subject matter is really extremely similar to what he mentioned, and the kind of developments that were, awarded the Nobel Prize this year. So, just if you look carefully at the Nobel Prize citation, there were really kind of two topics which came in reverse order in the little video. So the last topic, the second, was in fact the earliest historically, and that was what I guess people usually call topological phase transitions. Oops. Whereas the other topic, if you wish, would be topological phases of matter or states of matter. Actually, I prefer the term phases of matter. A state is sort of one thing, right? Which you can write as a theory, which will in nature never be quite precisely realized. A phase is a much broader family of states which are all connected continuously and which all show the same behavior, until you hit a phase transition and you run into another phase. So let's talk about topological phases of matter. And if you wish, you could say, of quantum matter, of quantum condensed matter. This will always be condensed matter physics, lots of particles sitting together forming, a condensed state of matter. And most of the magic of what we're looking at is quantum mechanics. So this is certainly a quantum matter topic. So but his first topic, topological phase transition, there was this picture that Hans Hanson showed about vortices that can exist as excitations over some ground state. So the name that goes with that is KT. You must have heard about the Kosterlitz-Thouless phase transitions, and again they were both on the ticket for the Nobel Prize of this year because of these discoveries. Whereas the names going with this second subject, the Nobel Prize, was again Thouless. That's why he got more than the others. He got half the prize and the others got a quarter. And then another set of names, which I should put together, that's the famous collaboration TKNN. I'll come to that a bit later. That's Thouless, Komoto, Nightingale, and the Nijs. And also Duncan Haldane's contribution that was awarded sits in this category down here. So I'll, in these lectures, we'll say close to nothing about the first part, the topological phase transitions, but let me just mention a few things about it, so you can hopefully place these two topics and appreciate a bit where they sit. So for this, let's say, the first topic, let's say the prototypical model where these things were studied and discovered is, for example, what is called the XY spin model in 2 dimensions. So this is a model describing spins, if you use compass needles that can, point in any direction in a plane, a 2D system, and there is, classical statistical mechanics of such system. Lots of these needles that are interacting a bit with each other, and that form a collective state, a collective spin state. And the famous hero, this vortex, this hurricane picture that Hanson showed is excitations in this kind of system which have a non-trivial winding number. So for example, you can imagine the whole thing being in a kind of boring state, which could be the ground state. Let's say everybody pointing in the same direction and nothing much going on. But then the interesting vortices that have this winding number feature would be, for example, configurations where, let's say, the spins have some kind of winding around a location in the plane. And as you can easily see, once a thing like this exists, you can characterize it by a winding. So the direction of this arrow of the spin, goes around from 0 to 2 pi if you go around the location of this vortex. So this is a non-trivial winding number configuration which you cannot continuously undo, so to say. You cannot undo a vortex by continuous deformations because this winding number will never go away. This is what I call, topological excitations. So the ground state here, so to say, this one is nothing special from the point of view of topology, no holes or no twisting or no crazy things, but the excitations have topological features. And for example, maybe a bit closer to your field of study, if you think, for example, of a sine-Gordon model, a quantum chain, with a potential that's like a cosine. So let me add that here as a second incarnation of the idea. So let's say sine-Gordon as a 1 plus 1D quantum system. You all know there are soliton solutions. They're actually extremely close to the instantons that this morning were on the menu with Stefan. Solitons in a sine-Gordon model are very, very close to vortices in a spin model. You can actually map one to the other with a bit of work. And there's similar physics going on there. So the question, if a sine-Gordon system develops solid excitations, yes or no, if they can proliferate at a given temperature, that's a similar question to whether vortices will happen, yes or no. And the famous discovery, again, of K and T was that, if you study systems like this here, you go to really low temperatures. Vortices are too expensive in terms of energy, or free energy to be precise. So they're too expensive to exist alone in the system. So you will never see lots of vortices sitting there. So if you some kind of temperature diagram, so here's that 0. For low enough temperature, you will see no vortices. And to put it a bit more carefully, that there may be a vortex sitting somewhere, but then there will be an anti-vortex in its surroundings, and the two together will be, topologically neutral. If the vortex winds +1, the anti-vortex winds -1, they can form a bound state. Such things are cheap and possible, but single vortices cannot proliferate at low temperatures. At high temperatures they can, because essentially there's a lot more entropy to be used. So at some point that you do see, at high temperature you do see, single vortices in such systems. And what happens at some critical point, which is now known as the T sub kT, so the temperature with a Kosterlitz-Thouless phase transition, is that you cross over, or you have a phase transition between the two behaviors. And so it turns out, this is a bit different from, let's say, more standard transitions in spin systems where you go from an ordered state to a disordered state. This is a more subtle case, but there are very similar phenomena. In particular, near this critical point here, there are singularities in free energy and all kinds of observable quantities. And again, it all hinges on these winding number features of the excitations, and that's why this name has stuck as topological phase transitions. But that's about all I have to say about that. So again, this was to be, let's say, complete with regard to this Nobel Prize story. But it's not my topic for here, and I think the connections between these two things are not that clear. I mean, this is a rather different topic. It's all about topology, but it's playing out in a very different way. So I'll actually take this away and make a clean sheet for my true story. So, you know, in a sense, you and I are from different planets in terms of the physics that we do. You know, I'm a condensed matter theorist. You guys are, if I understand correctly, all high energy theorists. So I'm sort of on my guard to make sure we understand each other. So please do the same. Please let me know if I use funny words that you can't place, or if I assume certain things that you've never seen before. Because I'm not quite sure what you guys do know and don't know. Maybe that's reciprocal. So actually, as compared to the lectures I gave last year, I'll spend more time on introducing things, explaining the context, making pictures, etc. But if you think that's too slow, also you can speed me up again. So let's have a conversation, now, and also if you wish, tonight or tomorrow morning, and I can adjust my plan to your wishes. So let me not dive into formulas straight away. They will come later. Don't worry. Let me make some kind of cartoon of the kind of system I'm talking about. So the modern story of topological phases of quantum matter, it takes place in many different situations, different dimensions. So there's 1D systems, 2D, 3D. There's all kinds of different materials that show these things. I'll be rather conservative and focus mostly on, let's say, the classic case. And there I'll go quite far, try to really get you to the advanced insights. And the classic case I have in mind, and I'll later specify more, plays out in 2 dimensions, 2 spatial dimensions. So if you wish, 2 + 1 quantum dimensions. I can imagine, a blob of matter, 2D matter, let's say a quantum liquid or some other quantum state, and there it sits. So it has a boundary. It fills a certain amount of space in my lab. So again, just to be sure, what are we looking at here? This will be some low temperature phase of matter. You only get into these phases if you make things really cold and really quantum. So all these experiments are typically done at low temperatures. It's going to be quantum matter. And again, I said that 2 + 1 dimensions. Okay, and I'm after a situation where this has this famous non-trivial topological nature to it, so to say. Now there are 3 alternative, let's say, pieces of information that I'll give you, which will express this topological feature. They're very different right now, I guess, but I hope that as the lectures continue, you'll see connections and you start appreciating all the structure. So one thing to say, which is actually what I'll make more precise as we go today, is you can characterize what's going on here. So the quantum state that all these particles are forming together by topological invariance. So this is straight to the heart of topology. So in this concrete case, there will be things called Cn sub n. C stands for Chern. These are Chern numbers, and there will be a formula which I'll probably have on the blackboard many times, but let me just do it right now for the first time. An observable quantity of the whole thing, which is some conductance, a Hall conductance, sigma sub Hall, will be expressed, and that's a magical formula as the quantum of conductance. This is E²/h. If you combine those and you look at units, this is a conductance 1/ohm. Yeah, that's correct. And then it turns out, the precise number by summing Chern number invariance. And the sum what that is will come later. But so there's a magical thing that you get conductances that are multiples of the quantum unit, and the multiples are given by topological invariance. So that's, I'm giving you one of my greatest results already. Right now, this is a fantastic formula that will be very important. And it's one way to express and appreciate this topological nature. If you like another approach to the whole thing, you can say, well, can we use quantum field theory to describe the essential behavior of these systems? In many cases, just a second, we can. So lots of insights in condensed matter physics, we can actually get our hands on using field theory methods. And that's another approach we can take here. But that's a question. And, okay, so I was kind of keeping that. N will be an index, n equals 1, 2, 3, etc., which labels the various bands. So there will be a band structure that's behind this story here. And the situation we're after, this special state of matter, arises when we fill the lowest so many bands and then keep the rest empty. And every band will contribute a number C1 of n to the total conductance. But this is all coming. I was kind of hiding that a bit from view right now. Okay, so if you're a field theory person, you can say, well, can I describe the essential behavior of this quantum liquid using field theory? Well, you can certainly try that. And what you typically get if the situation is topological, as we assume here, is that you get some kind of topological quantum field theory, TQFT, which expresses the topological nature of these things. And if you want an example, which will be actually quite close to the real thing if we continue, here's, for example, an action which will do the trick in certain cases. There you go. It knows about sigma whole, integral d2x, integral dt, because we're in 2 + 1 dimensions. And then, no metric, it's topological, epsilon mu nu rho, a mu d nu a rho. So that's Chern-Simons. It's the same Chern-Simons that Stefan had this morning, but it's the U1 version. For now, I'm just having a U1 symmetry, just charge. And so I'm writing this TQFT, and I'm telling you that it knows about the special features, and in a sense it knows about this formula, if you wish, but in a very different language. Yes? I would say in a very real sense, if you make, this is a picture, let's say, of the liquid in real space. If you make a picture, for example, in momentum space, it will have holes. In the same sense that the pretzels and the bagels of Hanson have holes. So it's not a statement about that excitations have funny winding numbers. It's the fact that the state itself, it's built, this will all come by filling bands, bands for free electron, quantization, and those bands will be funny. The bands will have intrinsic topological features. They're like Möbius bands rather than straight bands. So it's really in the very heart of the system. Yeah, I would say they're present in the ground state. So this state of matter has been built by, let's say, 10 to the 15 electrons per square centimeter, something like that. And what they do is they have, there's a free particle spectrum which has a number of bands. So I could draw a picture of that. Sort of getting ahead of my story, but that's okay. So if you would do the one particle problem, let's say in the circumstances that give rise to this here. So some 2D problem, there's maybe magnetic fields and maybe some other things. You would typically, you would go to momentum space, you would make a plot, if you put your momenta here, your 2 vector k, you put your energy here, you would discover, some kind of structure where there's various bands possible for one particle state, right? And I'll come a bit to that later, but this is the first place where we show this. And then, so for one particle, it could have a choice. It could pick which band it uses, and then it could pick also which momentum it uses. So it could say, I'm in the second band, and I have momentum here or there, so I'm sitting here. So now if you have 10 to the 15 particles per square centimeter, what they will do, they will all aggregate on the lowest possible energy state to make a ground state. So in the end, they'll fill, for example, the lowest band, and they will use every possible momentum that's available there. They'll maybe fill the second band. And the special situation that we're after, which will be some insulator, will happen when you precisely fill, let's say, the first n bands, and then you stop. So let's say your Fermi energy will be tuned to be right, let's say, in the middle of band n equals 2, n equals 1, n equals 3 up there. So if that's the situation, the formula here would be that you would sum over n equals 1, 2, and stop at that. You would only sum over the filled band, so to say. Okay? So that's how this state is kind of built up microscopically. And now the issue of this thing being topological, yes or no, is some feature about these bands over here, which is measured, if you wish, by this formula here, this C1 sub n. So the C1 sub n kind of gauges if band number n has a special topological feature to it, yes or no. And there'll be a formula later today even where we see how that goes. But the essence is that if all these things are zero, it's a boring non-topological state. But if one of them or more of them are non-zero, you get this thing to be non-trivial, and you get a finite sigma hole. And then if you look at field theory, if that's your language for describing the whole thing, the same sigma hole sits in front of this topological field theory describing the same liquid. Okay? And again, if sigma is zero, and you have just Maxwell theory for your U1 field and nothing special happens. But if sigma hole is non-zero, then this is the dominating term, and you get completely different response of currents and charges to external fields. Okay? So this is, so maybe to give you one consequence, if your TQFT is Chern-Simons, then typically if you would play, I'll do that later in the lectures. As I said, you can look at, let's say, expected values of currents through a formula like this. You take your ds, d, a, mu, so to say, and if you work that out for the case of Chern-Simons down here, you, for example, find that your currents, ji, will be like epsilon ij, this is my epsilon symbol in 2 dimensions, times ej, with a coefficient given by the Hall conductance. So once you have this here, if suppose you have gone far enough to convince yourself this is the appropriate topological field theory description, then you derive very quickly that if you put an electric field, you get a current which is transverse, via this epsilon symbol and has strength sigma hole. So then you discover there's a Hall conductance in this system. Okay, which is the same message that you had here, but in a different kind of approach. So that's very nice. And again, it allows us to use all kind of field theory technology to play the game this way and discover the important physics from that. One more way of viewing the situation that I drew would be a more physical one. I mentioned we are in a situation that's like this, so where there's a bunch of completely filled bands and then completely empty bands on top of that. So if you wish, this is an insulator. It will take a finite amount of energy to reach, to excite a particle from a filled band to an empty band, and that means we call this an insulator. Which, so if you wish, usually another word for these things is this is a topological insulator. So that's fine, but you can already sense that there's something funny going on, because I explained to you already in 2 ways, at least I tried, that there is a non-trivial response to even a very, very small electric field. If I put a tiny bit of electric field, I get a tiny bit of current, which is non-zero. And this is hard to understand if you look at this picture, because you would need finite energy to reach an excitation at all. So something else is going on. Somehow this whole response is carried by these filled bands alone, rather than by exciting to an empty band. And if you look at this more physically, how can this be? So if you where are these currents located? How are they carried? They're not so much in the bulk of the system, but they tend to sit at all kinds of excitations running around the edge of the system. So a characteristic of most of these systems, not all, but most of them, is that there's lots of action, if you wish, at the edge of the system, at the boundary of the system. And typically, even if the thing is insulating away from the edges, you know, there's modes running around the edges which are actually gapless. Gapless edge modes. And if you analyze, once again, I'll be doing this in concrete examples later on, sort of where these currents are located, you can, in certain cases, have a very convincing physical pictures where the currents are carried by edge modes rather than by bulk excitations. And then the whole picture can be kind of, you know, made consistent. For example, if you look at this Chern-Simons formulation over here, and you wouldn't know about edge modes, you would actually discover them, because if you check the gauge invariance of a Chern-Simons action, you may have done that at some point, you know, you need a partial integration, which is problematic and which actually fails on you. So the complete gauge invariant field theory, that's this thing in the bulk, has to have some compensating terms at the edges to save the gauge invariance. And if you formalize that, you'll discover precisely these gapless edge modes. This is the kind of reasoning that Xiaogang Wen applied to these systems. So the whole thing is nice and consistent. And also, you know, if you have this picture over here and you say, well, there's somehow no room for currents and excitations, gapless excitations, well, this picture isn't completely right if there are actually boundaries to the system. So the picture there supposed, you know, translation invariance, meaning there are no boundaries, or you're on a torus. If you're not and you're on a system with actual boundaries, there'll be modification to this picture, and there'll actually be some modes that are coming in that will be crossing this Fermi energy, and that can actually carry some of these currents. So in the end, the story is very nice and consistent. There's various ways to look at it, very mathematical with invariance, field theory type like this, or, you know, sort of with physical hand waving pictures where you say where are the currents, how are things connected, and in the end they all agree on the outcomes, and they better agree because these are observable quantities. This thing you can measure. So this is actually flashed in the talk of Hans Hanson, this famous sharp quantization of the Hall conductance. That's this formula, and you can measure that with amazing accuracy, and it, you know, it works out right. So these things have to be valid to extreme accuracy, actually, and that's a very beautiful story. Yep. So does this make some sense to you, or am I already too far from your everyday life? Yes. In a sense, there would be an extra layer of complication. So, if you wish, the cheap excitation, so to say, that are gapless, so that I can excite with very little energy, will always be edge modes. So if I have my system and I try to excite it, the easiest way is to put some fields near the boundary, and you'll generate these edge modes. You can also make, you know, bulk excitation away from the boundary. They will cost finite energy, and in a sense they are like vortices. So I can make them, you know, somewhere here, and I can do all kinds of things to them. But those are, you know, not so cheap excitations that cost finite amount of energy, and they're really a lot more like, you know, moving a particle all the way up to the next band. And it depends on the kind of physical situation that you have. If you want to focus on bulk excitations, or rather not. For example, you know, if you like to do topological quantum computation with these systems, which is one of my favorite topics, you would actually, you know, put excitations away from the edges in the bulk, try to open some register and braid things around and do things that way. But it's, in terms of low energy physics, the thing that hits you first are these edge modes. And you see, maybe that's you know, I made my 2+1D picture, but this this importance of things at the edge is actually much more universal. In a sense, it was discovered by Haldane, which is also mentioned in the Nobel citation, in the 1D case. So if you have a 1D system, then your bulk is just a segment of a line, but then your edges are the 2 points at the ends. So there's stuff here and there's stuff here. And so Haldane studied a system which was a spin chain that is actually built from elementary spin 1 magnets, right? So if you let's say the simple spin chains are built from spin 1/2, but if let's say your atom or your fundamental spin is spin unity, you can build a spin chain, and if you give it the standard Heisenberg couplings, it will be in a gapped phase, so it's like an insulator. It takes finite energy to excite something in the bulk. But then what Haldane discovered, that people after him worked out, is that at the edges of these chains there are gapless modes which actually spin 1/2 excitations, which is remarkable because the stuff on the inside is spin unity, but somehow at the end things fractionalize, and there's these spin 1/2, one on each side, which are the gapless modes of that case. So this was Haldane early on, 82, 83. In the 2D case, as I mentioned, the edge modes are kind of going around an actual edge in 2D. But if you think 3D, we now have these 3D topological insulators, which are really three-dimensional bulk material. And there the statement is again that on the inside, away from the edges, they're insulators. Nothing happens in terms of current transport. But at the edges, which are now complete surfaces, these are conducting states. These are metals, if you wish. So these TIs, as we have them now in 3D, protected by time reversal, blah, 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 they have extremely interesting surface states, which are a lot actually like the kind of things happening in graphene, in two-dimensional, good conducting materials with magical properties. Okay, so this edge thing is universal. It sits in 1D, 2D, 3D. And, we even think about going to 4D and studying things like quantum Hall effect in 4 dimensions, where there would be 3-dimensional edge stuff happening there. Okay, other questions? Yes? Yeah, so that would, of course, if you want to make a thing in a controlled manner, you would probably want to go to the band structure and study what's going on in these bands, depending on all kinds of parameters. And then in certain cases, you can play with models where there's parameters, and if you tune them through a critical value, you go from non-topological to yes topological. Okay, so certain materials happen to be in a situation where bands are non-trivial. For example, this 3D situation happens to occur. There's certain compounds where if you do band structure calculations, you discover you're in this special case. In other situations, you actually allow yourself a few knobs, for example, external magnetic field or spin orbit coupling or other quantities, and then you discover that there's certain parameter spots where these things happen. And then you can really tune into and out of those phases by external control. Other questions? So please ask if things are not completely clear. Yeah, this will be coming back as well, but so roughly speaking, the program I carried out in this situation would be that I have my fundamental constituents of my liquid. Let's call them psi or psi deca or things like that. For example, my electron fields or my cold atoms or so. And there would be some microscopic description, which is all these bands, all these things. So some action that you could play with. But now if your interest is in the response to external gauge fields, or electromagnetic fields, you would typically, couple this thing. So you would make an action where you couple your psi dagger to, let's say, a mu. And then what you can do, for example, is integrate out your matter field's psi dagger, which makes sense because you're an insulator, so it's a good strategy to do that. And then that brings you to an effective action S of A, like here. And once you have that, you read off response to external fields through formulas like this here, and you discover the magical relations that you're after. And so the big question is, if you follow this program, is the action you're going to find, is it of this type, or is it, let's say, of the Maxwell type? And for example, if your system has time reversal invariance, this could never happen, because this one breaks time reversal symmetry. So if my system that I'm looking at here would have time reversal, I can never have this. And I would probably, the leading term in this would be a Maxwell action, and there would be kind of standard response, nothing special. So depending on details, this term can actually pop up, and if it does, it gives you very different phenomenology. And then if you work out when does it happen, it happens when the bands have this mathematical structure like over there. Okay. So it's all coming back. This was just so I thought I'd do it in stages. So first, the talking head of Hanson, and then this cartoon with a bit of things on the side. But I'll make several new starts to really bring the story carefully, step by step. But the first thing I want to do right now is actually talk about some experiments, because the beautiful thing about this this field is that I think it should be in physics. There's always theory and experiment, and there's always, let's say, ping pong between the two. Sometimes theory is first and experiment follows. Sometimes it's the other way around. And this is a field of research where the things are really extremely intertwined. And roughly half the time there's a prediction and the experiments confirm it, or explain that it's not well conceived. And the other half of the time it's the other way around. And I think the progress that we've seen in, let's say, the last so many years really was so fast, because there was continuous back and forth between theory and experiment. So I selected for you actually 6, well, I would say, key experiments, key discoveries, key papers, and in each case I'll use 2 colors for, let's say, experimental observations and theoretical thoughts about these things. And you'll see this what I mentioned in action, this back and forth. And so what I focused on here, so I call this, experiment and theory. And I really focused on 2 things. One is what I call the quantum Hall systems. And the second would be what I called, I'll use that language, TIs, so the topological insulators. Which, this is in a sense a subset of all the developments, but it's already quite rich. So I decided to focus on that. So, and here's a few things. I mean, this is my personal choice. It's not objective. It's just a few things that I think were really nice and important. So there we go. 1980, discovery of the integer quantum Hall effect. As mentioned by Hanson, Klaus von Klitzing did that. The famous steps in the whole conductance of electrons under very special conditions. So that was an experimental paper. 1982. The TKNN paper, Thouless, Kosterlitz, Nightingale, De Nijs, introducing this notion of topological quantization. And I would say, this paper explains a lot about the observations by von Klitzing. I wouldn't say it explains all of them. There's, still subtle things about disorder and stuff like that. But it certainly got a large chunk of the insight needed to explain this amazing experiment. Okay, so that was one pair, let's say, of back and forth. 1982, there was the discovery of the fractional quantum Hall effect. I'll give you more later. It's a different thing. It's a different phenomenon. Theory came within a year, 1983, Bob Laughlin wrote an amazing paper, explaining what was going on in these experiments in the fractional case. And I guess that if you want to say that in 2 words, what he introduced were special fractional quantum Hall wave functions. So this was a many-body effect explained by a many-body wave function, which is very rare. Usually we have different techniques and we cannot go to the essential behavior of quantum many-body using wave function, but he did that and he got it right. So that's another, a nice pair of things. In the same line, but more speculative, a third, if you wish, a third round of quantum Hall discoveries was something that followed in 1987. When people, what they saw was what's called the 5-half quantum Hall effect. I'll tell you more about that later, but there was an observation which didn't fit in the understanding built up after Laughlin and followers, that there was this kind of mystery observation. And what many of us believe, but which is unconfirmed, is that this was a glimpse of a thing called, so maybe let me actually put again the theory, follow up on this, which was 1991 and later. That was started by Moore and Reed. Greg Moore and Nick Reed. I guess you know Greg Moore is a high energy theorist, but he made a little excursion into condensed matter with spectacular results. So there's this Moore Reed paper which talks about what are called non-abelian quantum Hall effect. And so on paper that works fine. There are wave functions that certainly have that kind of behavior, but the belief is, or the suspicion, I guess, that what has been seen in 87 and later by many groups is that these observations actually reflect this kind of structure that we know on paper from the theory side. But again, this is much more speculative. I should put some kind of question mark because it's unconfirmed. We don't know. It could be something else. It's still under investigation. But it's again a very nice combination of theory and experiment. 1988, I should use my other color, because it's theory. The theory now came first. So this is the thing which was briefly mentioned in the video. That's Haldane writing a paper. So I think Hanson said it this way, that he had something like the quantum Hall effect but without magnetic fields. So in modern day speak, we call these things Chern insulators. And they definitely started with a theoretical investigation. So the thing people now call the Haldane model, which is actually nice and simple. It will be my next item on my list of topics in the course. I'll go through it in quite some detail. And you'll see that it has all these features, including a quantized Hall conductance that we knew from the quantum Hall effect, but it lives in zero magnetic field. And these things were followed up, a bit later. I think if I follow the Nobel information paper, they mention 2013 as the first time this kind of behavior had been seen in experiments. So there were experiments 2013 and onward. I think the first of them were thin films of some Ti material. Okay, so this was a theory invention that took 25 years to actually be realized in experimental settings. Okay, and then 2 more today, which actually some very famous things. So I should again, let's see, first go in red. So Bernevik et al. Bernevik, Huge, and Zhang wrote a theory paper 2006 about a thing they call the quantum spin Hall effect. Which is another example of these topological phases. This is in 2D, but it's for particles that have spin up, spin down, so it's a bit different from what I had before. And this was then, this was 2006. And this was, followed quite soon after, 2007. Paper by, I think it's Koenig et al., the group of Molenkamp in Würzburg. where they found these things. So they found experimental evidence or confirmation that these things are for real. This was in mercury telluride type materials, some quantum wells designed for the purpose. They checked the whole thing and they gave confirmation. So that was again, theory comes first, experiment follows soon after. And then one last thing to give you another highlight in this story, 2007, Fu and Kane. They proposed, they predicted these things that I already mentioned in 3 dimensions. So they said, special compounds in 3D. And I guess the one they proposed was, for example, bismuth telluride would be such that their bands have, topological twisting and would give rise to 3D topological insulators. So they said that, and they actually said exactly, you should investigate those materials and you should do it with RPES, and then you should see such and such experiments. And this was all done by the Hanson group in Princeton quite soon after 2008 and going. And there's discoveries of the 3D topological insulator materials. And again, I think the first experiments were on these bismuth telluride, bismuth antimony type compounds. Okay, so I think this is quite a list. Since we started this way, if you look at Nobel Prizes, this was a Nobel Prize for von Klitzing. This was a Nobel Prize for Sturm, Tsui, and Laughlin, the 3 of them. So they were happy to get a theory experiment. And now, this is a repetition from what I told the other audience 2 years ago. But now, since that time, this thing here, the Haldane Schoutens later story, has been awarded a Nobel Prize, and also the TKNN analysis over here is in that list. And I think many of us expect that, in a few years going, there will be 2 more ends somewhere on this board here, because the more recent developments were left out of this year's prize, but they've been spectacular enough to grant another awarding. So who knows? At some point there will be more. And I think if this thing is ever for real, I would, it would be my favorite for a Nobel Prize, because it's really beautiful and deep stuff that we would like to see confirmed. So again, it may be a bit away from your usual business, but this is really, I would say, spectacular and beautiful physics. And I thought, I should mention where it came from. It was invented on paper, yes, but also because people saw certain things in the lab, and they started thinking about what those were, and then the thing developed quite nicely. So in retrospect, there's this question: why didn't somebody, discover or think of topological insulators, 40 years ago? Because in a sense we knew enough to make such a discovery. Nobody did. It's a bit of a mystery, but it took a long time to get there. I have a few more things by way of introduction, which is, let's say, about the toolbox that we use as, let's say, as matter theorists facing all this stuff. I think that's actually quite important, because I can at some point I'll start doing computation on the blackboard. You can follow minus signs and factors of 2 and so, but none of these computations is kind of obviously the right one to do, because the obvious thing to do would be write, let's say, the Hamiltonian or the Lagrangian for your many-body system and compute through the whole thing, without any approximation, without any hindsight. And the message is, you can almost never do that. It's too difficult. It's too complicated. There's always lots of particles close together. They all interact with one another. There's all these quantum principles, and the whole thing is extremely hard to control theoretically. So it's a real headache, if you wish, to do quantum many-body theory and to not lose control, because it's too difficult. And every time you look at a certain type of problem, you should really think twice or 5 times before you commit to a certain approach and work it out and spend time on doing that. Okay, so I've got a few general remarks on this thing. So we're talking condensed matter theory in general terms, or maybe I should be a bit more specifically, maybe talking quantum many-body theory. So how do we do that? And how do we choose the right kind of tools if we're interested in these topological features and try to decide how these systems behave? So I would say, there are easy cases, and the amazing thing is, I think 4 out of the 6 examples that I had on the blackboard are in the easy category, and easy in the sense that they are about free particles. You can get away with neglecting interactions. Okay? And in that case, things are relatively simple. So suppose you have free particles, which means if you're talking electrons, you're actually throwing out, let's say, Coulomb interactions. You simply forget about it. You assume you can get away with an approximation where you treat things as free particles. Okay, so what are these particles? Once again, most of the time they're electrons, but in very special circumstances, maybe they're in 2D or maybe they're under strong fields or whatever, but they're made of electrons, so these are fermions, obviously. And then increasingly, we're studying systems where we look at many-body physics of cold atoms. Cold atoms are, a famous case which we can control better and better. And we can actually, since a few years, really study many-body physics of interacting cold atoms. And then, obviously, those can be either bosonic or fermionic either way. So there's, in a sense, 2 versions, and they have their own behaviors. Okay, and now just to be sure you remember these things. If you're free particles and they're type boson fermion, you know what to do, right? If they're bosons, okay, you go to the one particle problem, you solve it, you find a bunch of energy levels for the one particle, ground state, and then lots of excited states. And if you have 0 temperature, no interactions, nothing going on, what the system does, all the bosons jump into the lowest energy state down here, and they make what would be a BEC, a Bose-Einstein constant. This is what bosons like most. And again, if you simplify things to the extreme, so there's no interactions, no temperature, no nothing, this is what they will do. And sometimes in nature we see situations that are very close to this, and we see BEC and all that happening. If you have fermions, this is the big case, you do the same thing, start with one fermion, do the one particle problem, solve it, find a bunch of energy levels, or maybe a bunch of bands if I'm more careful in more dimensions. And then what your fermions do, they fill the lowest so many states until they all have found a place, and there it stops. And so they build what's called, a Fermi sea. And at the top of that sits a certain energy, which is Fermi energy. And that's what they do. Okay. Yep, and if you like thinking formulas, if you have wave functions, psi sub I or something for these single particle states, then you make a Slater determinant, so the product of all of them, and you anti-symmetrize, and that's your many-body state describing the Fermi sea. So that's all very easy. But again, this so the integer quantum Hall effect that I mentioned, so the first of my 6 items is essentially a free electron problem, where you can get away with a picture like this here. And then these TIs, the recent stuff, so this quantum spin Hall effect and the 3D TIs, you can also approximate the description quite nicely by making this story over here. And also the Chern insulator story of Haldane. So this also means that in these lectures I can be quite precise about those cases, because I can steer away from, hard to control interacting quantum many-body situations. Okay? So if interactions are essential, and you cannot get away with this kind of picture, which happens a lot, of course, in actual condensed matter systems, then you're faced with doing 10 to the 15 per square centimeter or 10 to the 24 per cube centimeter particles, fully interacting, quantum mechanical, etc., etc. And then there's a whole list of strategies, or if you wish, tools that we have available to go about such situations. And in a sense, this is the art of being a condensed matter theorist, to be able to work with all these options. So let me just give you a few bullets. So of course, what you try to do is solve the whole thing exactly, even if there's interactions present. And sometimes you can. Sometimes you can. So analytic solutions. So what I would say here, two things. First of all, this is highly limited. Usually it's in one dimension, and then even then you need special type of interactions, so that, for example, a beta ansatz can be made to work or something similar. But it's also very rich. So having studied all these special cases, we learned a lot of physics. I mean, spin charge separation, all kinds of beautiful things we understood or we discovered following analytic solutions. So sometimes this is what you can do, and that's perfect. But then, most of the time, you cannot do that. You have to make approximations, and then it all depends. And then it's there's a whole list of things you can try. For example, you can do all kind of truncated Hilbert space approaches or all kinds of things. And then it really matters. Sometimes it's fantastic. For example, BCS theory for superconductors is a mean field theory, so it's not exact. You throw away lots of fluctuations, but you keep a mean field ansatz, which for, let's say, a BCS superconductor has all the essence. So you understand all of, let's say, traditional superconductor physics on the basis of a mean field model. It's just fantastic. But there are cases where mean field theory is completely wrong. If you assume it, you work it out self-consistently, you get conclusions, they're completely way off the actual physics, because it's a case where mean field theory is just not a good option, and you have to somehow understand that. So this is, I would say, very good sometimes, but also difficult in other cases where it sends you in the wrong direction. Numerics, obviously, that's a whole field of study. People have devised lots of methods to do numerical analysis on quantum many-body systems, and again, it depends. All kinds of details. If you're studying, for example, multi-boson systems, usually things like Monte Carlo are very good, and you can get very accurate results. Fermions are much more difficult. In many cases, you cannot properly treat them using numerics because of minus sign troubles that keep you away from good solutions. And again, it is a very rich field, and depending on circumstances, it gets you where you want to be, or it's not good enough and you need something better. Other thing, quantum field theory methods. That's a nice one. We know so much about quantum field theory. A lot of it, because we developed stuff in the context of high energy physics. And what's really nice and gratifying to see that many of the insights that somebody derived, let's say, in high energy context, are meaningful and important for a different context, such as the one that we're looking at here. So I mentioned this TQFT, which is also something considered away from low energy physics. A thing I'll be mentioning and using a lot in this course will be conformal field theory, CFT, which may surprise you because this is about critical matter, not about topological insulating type things. But there is beautiful connections, and I'll actually rely a lot on CFT techniques to get my hands, for example, on the cases that I'm not in this easy class here. So this will be important for me here. And then you can keep going. I have one place left. I can put ADS CFT here. Some other spectacular approach that has learned us new things over the years now. But to finish my little story, maybe I put that here then. So these two topics that I mentioned, which were not covered by the free particle case, so the fractional quantum Hall effect, and also this non-abelian case, non-abelian quantum Hall effect. So used a bit of some exact things for small systems and a few other techniques, but I'll mostly rely on these CFT methods. So that will be the workhorse for me to understand stuff for those interacting cases, which are really difficult otherwise. So yeah, that much about my tools. Are there questions here? Are there things that I mentioned that are mysterious to you, or how about CFT? How many of you have some experience in conformal field theory? Okay, that's good because I'll need some of that, but I'll also make introductions to for the rest of you. Okay? Okay, then I'll keep going. I'm still introducing my subject, as you understand, going really slow. I'll give you my plan for what I intend to cover. Which is mostly telling you about what I plan not to cover. You know, the field is huge, and I have made all kind of choices what I think I can fit in my lectures here. But that means that certain things that you may have heard about and you were excited learning about this week are not even on the menu. I also do this, I also give you my list to be flexible, so if you know, enough of you complain that one item is missing and should really be there, you know, please make a request and I'll somehow change my plan. But the plan as it stands today is that, you know, I'll have, so the plan for this week, my focus will be mostly on these, you know, quantum Hall type systems. Now, for a number of reasons, they were first historically, and they're extremely rich, and they illustrate, you know, many of the important physics. And this includes, so by quantum Hall type, I also include these Chern insulators that Haldane later wrote. And my methods, once again, I'll talk quite a bit about these topological invariants. And I'll try to use as much as I can, let's say, the TQFT approach and also the CFT methods. Okay, and this also means that I'm not doing certain other approaches that are by themselves very interesting. Okay, so now, not covered. Lots of stuff. For example, all these spin systems. I mentioned briefly Haldane's analysis of spin 1 chains. But that by itself is a beautiful topic. You know, why is there a gap if you have a spin chain with integer spins and not a gap if it's half integer spins? Things like that. Spin systems, you know, the way you handle them using, for example, sigma model language, sigma model field theories with theta terms and stuff like that. So not on the agenda. All these things which are, I guess, technically called symmetry protected topological cases, which includes, for example, this quantum spin Hall case and also this 3D case. So those only survive because in that case there's a Z2 symmetry protecting time reversal symmetry, Z2, protecting these phases from, you know, going trivial. It's nice. It's also lots of recent action is happening, but not on my list. And then another thing is, you know, there's lots of attempts at classifying these states. And for example, there's a famous result if you say, well, let me imagine the whole thing is built from free fermions. So not bosons, but fermions, no interactions, no lattice background, just free fermions in a continuum situation. Then, depending on details, in particular the symmetries that I mentioned here, you can make a list of what's possible in terms of these phases. So one item on the list would be quantum Hall type system, but there's, if you wish, a longer list. It's known. It goes under the name of Table of 10. You may have heard about that. It's beautiful. There's lots of mathematics in that table. There's lots of physics in that table. But again, I've so far decided to not cover it here because it's a big topic that would take me too much out of my way. But if you're all disappointed, let me know and I'll try to blend it in one of the later sessions. Okay. One more thing and then I finish my introduction. I'll give you a little breather of 10 minutes or so. My sources, you know, a good journalist never reveals sources, but a good scientist reveals sources all the time. So let me tell you where I get my information from, you know, aside from obviously literature, research papers. So there's 2 books that I recommend. So sources, books. The first one is this here, Eduardo Fredkin, Field Theories for Condensed Matter Physics, second edition. This book has been around for a while as a first edition, which was about half as heavy as this one. So there's a rather recent second edition, which is fantastic. So he added all the recent developments, made it, even more readable and better. It's extremely rich. It's hard to read. He says it's not a textbook. It's more like an encyclopedia of the subject. But I based some of my story here quite closely on how he writes things. So, it's really all about the field theory approach to things. So that's maybe close to your natural language, so to say. The second book that I recommend is, I guess, the first book on the market really about topological phases, topological insulators. That's written by André Bonnevik, one of the founding fathers. He was already on the blackboard as one of the pioneers of the field. So he was quick to write a book that's available since about a year or so. And it's nice. It's rather technical, but it has stuff and you can read from there. It has problems which are very difficult. So there's two authors, Bernvik and Huge. So that's books. There's reviews. And two of the early reviews that are kind of celebrated. There's one by Kane and Hassan. Let me call it C. The same Kane that I mentioned, Charlie Kane. And Hassan is the experimentalist at Princeton who was the first to do the RPS measurements. The photo emission experiments to confirm the 3D TIs. So that's a very nice review. It's a bit old. It doesn't have the most recent developments. And there's another one by Xusheng Zhang, another founding father, together with, I think, with Xi. And these are both, reviews of modern physics. Okay. And then two more sources which are more like lecture notes. What I like is, this Mr. Hanson that we looked at in the video, I think, I'm not sure, but I think he authored, the advanced background information that the Nobel Prize always gives. So that's a nice review paper on the subject. It's really well done. So that's the thing I recommend you read. You'll see the same pictures that he showed in his slides in that story. So be sure you look at the advanced. There's also some kind of press release for, let's say, for journalists, which is a different type of language, but you definitely want to go to the advanced technical story. And then finally, so 2 years ago, I wrote lecture notes for my lectures here in the SFT school, and they're still on the web, and if not, I can maybe repost them for this year. So I may actually do them again, depending on, if I deviate more and more from that story, I'll make a new story. But if I stay rather close, I'll maybe leave them. But they're certainly available, so you can look at them. So that's my lecture notes by myself. So that's, GGI SFT School, 2015. And they have a certain style. They're sort of infographic style lecture notes rather than long computations. So yeah, I think with all this, you should be fine. You should be able to trace what I say and read back the story. And I'll I guess indicate a few times while my story continues where I get stuff. I'll maybe say this is chapter 12 from Fredkin, this is chapter 3 from Bernevik, things like that. So that's my plan. I'd like to do a little break. Let's see, I'm supposed to stop at 5. How about 7-minute break? And then I'll continue after that.